we've talked about how the structure of a molecule or the symmetry can define the electronic structure, like the energy of the orbitals and our molecular orbitals. But let's talk about what dictates the final shape of the molecule. And so, for example, we've seen before that something with, four, like a metal center with four things on it could be a multiple. Like, could be tetrahedral, it could be square planar. There's a number of different geometries it takes. So what dictates the shape of a molecule is dictated by the energy of the HOMO. The HOMO dictates geometry. Meaning that if in one geometry, the HOMO, so the number of electrons, would be in a higher lying orbital with higher energy than a different geometry, then it would choose a second geometry because the molecule wants to be more stable. It wants to lower the energy of electrons. If, for example, the HOMO is then the same energy between the two geometries, then you'd pick the next highest molecular orbital to fill that. So here's an example. Let's do like a putative MH2 molecule. So a first row dihydride. This could be some sort of main group element. OK, so this dihydride, if you have two things on something, it could be bent or it could be linear. You have two options, although I guess that angle could change. But let's take that first linear example. So if we have our linear example, if we were to make our MO diagram, so here's the metal, here are two hydrogens. I won't go through it, but for this linear geometry, this is d infinity h. So if you were to use the character table, what you'd get out would be that the s orbital of the metal is going to be sigma g. Remember, G stands for Garada, for a system with an inversion center. So this is symmetric inversion because it's an s orbital. And our p orbitals are all anti-symmetric because if you do an inversion for any p orbital, it changes phase. So they're all going to be ungarada. So what this ends up being is sigma u for our pz down this h vector. And then we also have pi u for our px and py orbitals. And then for the hydrogen atoms, we have two degenerate hydrogen atoms, two degenerate salts rather. And these are going to be sigma g and sigma u. And then so the sigma g, of course, is Garada, so it's going to look like this. Our sigma u is going to look like this for our two hydrogen s orbitals. So if we then generate our MO diagram, so we have sigma g's that match, we'll form bonding. Here's our sigma g. Remember, this is going to look like this. Sorry, imagine this is dashed. OK, and then and we have our antibonding sigma g, which I'll put up here, strongly antibonding. Sorry, this is also dashed. Sigma g star, right? This is our out of phase combination. And then we also have I'll draw this in yellow, sigma u. Right, this goes down less because this is matching up with the p orbital energy. So this one is our pz. And then we also have our antibonding sigma u star. Sorry for the overlap with this molecule. Right, so this sigma u star looks like this. And then, of course, we have our non-bonding pi u. So this is non-bonding, so this is just going to be our px and then our py. So this is our MO diagram. We don't know what metal M is, so we don't have electrons yet, but this is what our MO diagram looks like. So, and I've drawn the pictures of the corresponding orbitals. So what happens if we then think about changing the geometry? We're going from this linear MO diagram to our bent MO diagram. So what we can think about is how each of these individual molecular orbitals should change in energy when we do this bending. So what happens when we bend? So let's first consider, I guess, this pi u example. So this pi u, which we'll call px, So this is going to, currently this looks like this, right? And then we have our hydrogen atoms that are in the nodal plane, so there's no interaction. But if we were to now bend it down, so upon our bending, this moves down, so we could, oh, sorry, take it back. I'm going to use the shaded one here. So here's our shaded one. So the shaded ones move down. And then we have our px. So overall, you can see this goes from no interaction, so this is what was our non-bonding pi u, and then we bend it down. So this overall is stabilized. And also point out that this could be mixed. Can mix with our sigma g, right? So this is just like, because we're going from this d infinity h pi u irrep, once we get to this bent C2v geometry, now we have this p orbital, which I guess now becomes our pz. We've changed kind of our coordinate system, but it doesn't matter because this is an A1 symmetric irrep. So this has got to be able to mix with our other A1. So our sigma g over here becomes an A1. So when we mix it with that sigma g, so I'm talking about this one, we could still get to that same, so we're going to mix our sigma g plus our px over here. And then what this becomes is so it's this combination plus this bent combination. So overall, this will become still bent. And then we could then draw the mixed combination like so, right? This is our mixed, stabilized. So mixing the pi u and the sigma g. This is stabilized. And then so we can relabel this in the C2v geometry as A1. Ta-da! OK. Similarly, if we take, let's say, our sigma u, which is this one, and then we bend it, our final product will look like, here's our, so these stay the same. We're keeping all the different atomic orbitals in the same phase, but then we just have changed the connectivity by moving the atoms around. So you can see we're going from this linear geometry where we have really good overlap between this p orbital that's pointing directly at the s orbitals of the h atoms to now here it's still in phase and bonding, and sigma bonding, but you see that the overlap is less good because the p orbital is no longer pointing directly at this. So this is destabilized. So this has to go up in energy. So bending makes this sigma u orbital go up in energy. And I'll also point out that this is going to be our B1 representation in the C2v point group. OK, so we can do the same thing for our other orbitals as well. So let's say we take our pi u for the py. So this was degenerate with this px pi u in this thing. But we saw that for the px pi u orbital, it was stabilized. But this one, oh, sorry, I meant to go from the linear. So in the linear one, there was no interaction. So again, we had like kind of our hydrogen atoms in the nodal plane. But if we bend it, our hydrogen atoms are still in the nodal plane, but they're going down. So overall, there is no change in this energy. And this was, if you remember, this was the B2 symmetry irrep, which was also a non-bonding centered on this middle atom. OK. And then for now, we look at our antibonding orbitals. So we have our sigma g star, which again can mix with this px. Or I guess if you want to call it, for this geometry, it's a pz. But it doesn't matter. This p orbital that's pointing straight up and down in the plane. So we have, so here again is our kind of px, which had our nodal plane hydrogen atoms. And then now when we bend, so now we can have our mixed, like so, So this is mixing with the sigma G star. This is the out of phase combination. And so overall, this going from here to here is overall destabilized compared to the PX. Although, yes. And then so this is more antibonding. So this is destabilized. And then this is the B1 star. OK. Oh, sorry, this is the A1 star, rather. Ah, mistakes everywhere. A1 star. And then lastly, we have our sigma U star, which is going from this antibonding combination to the bent one. So again, here, so again, this antibonding orbital has really good overlap, so this is very destabilized. So by going to the bent geometry, we are overall stabilized. We've gone down in energy because we've removed some of the overlap of these out of phase orbitals. And then this is our B1 star. Great. So now we can see that changes in geometry stabilizes some orbitals and destabilizes others. So what we can do is we can plot what's called a Walsh diagram or a correlation diagram to see how changing the geometry affects our overall energies. So give me 2 seconds to erase. So here's our correlation diagram. What we can do is on the x-axis, we can plot our phi. So this equals 180, linear, and this is bent. So I'm not specifying the angle. So this phi I'm talking about is this angle here. And then the y-axis is just energy. So at the linear one, we had that same ordering of orbitals that we talked about in our MO diagram. So at the very bottom, of course, we have our A1. And then we had our, oh, sorry, oops, this is linear. So the very bottom was sigma G. And then we had our sigma U. And then we had our non-bonding pi U's, which are degenerate. And then we had our sigma G star, and then our sigma U star. And then we can just stabilize and destabilize as we specified over here. So first of all, we know that our sigma G was overall stabilized because due to mixing. So we could draw kind of a line. Let me change color. So somewhat, and again, there's no quantitative value here, but we can actually kind of see. And then so our sigma U bonding was destabilized upon bending. So this has to go up in energy. And then this became our B1. Our pi U split, right? One of our pi U's was stabilized upon mixing. The pi U changed. So this was our B2 that was unchanged. And then the other one was stabilized. So this is going to cross downwards and become A1. And then our sigma G star over here was destabilized upon mixing. And then our sigma U star was stabilized. So we have our stabilized sigma U star, which was B1 star. And then our sigma G star was destabilized and then became our A1 star. So overall, this should final ordering should match what we actually got for maybe for the MO diagram of water, which is a C2V main group dihydride that's bent, right? So the more you bend, the more extreme these changes will become. So what you want to do, if you want to compare like which one's going to be more stable, is start filling in electrons. So for example, I just mentioned water. Water is a main group dihydride, and then so this should have 8 electrons. So when we start filling in electrons, let me change color. Let's do blue. So we can start from the right because we know it's bent. 1, 2, 3, 4, 5, 6, 7, 8. So this is our filling in. If we fill in 8 electrons over here, 1, 2, 3, 4, 5, 6, 7, 8. you can see that even though our HOMO doesn't change energy, right? B2 was this pi u, which is not changed. So again, when we think about which one's more stable, we can then do the next highest electron. We can see that for the bent geometry, this B1 is still lower in energy than the B2. So water is more stable in this bent form than in the unbent form, where this, so if you want to think about the second highest, the HOMO -1, this one is lower in energy than this one, which is degenerate with the B1. So that's why water is bent and not linear. Which is, again, a slightly different way of thinking about what you previously thought about, which is VSEPR. But this is a kind of a different way of getting to the same results. But it's also really useful in interpreting a lot of different geometrical changes. It's all about the stability of your electrons.